right? So I will be continuing the last week's content. So we discussed about Maxwell's law in the last class, and we derived the wave equation using Maxwell's laws. So we used that Maxwell's law to prove that electromagnetic waves can be propagated due to the interaction of electric and magnetic fields. Right? We used Maxwell's law to prove that we can have a propagating electromagnetic wave is generated due to the interaction between the electric and magnetic fields. Right? So we derive the wave equation under certain assumptions, and those assumptions were that the wave is propagating in a homogeneous medium, and it is that medium is having a certain permittivity and a permeability. So we derived the wave equation in the last class, and in today's class, we are going to discuss about the simplest form of electromagnetic waves called uniform plane waves. And we are going to use the uniform plane waves to identify some parameters of the electromagnetic waves. So parameters such as the propagating speed, the impedance of the medium to the propagation of the electromagnetic wave, and so on. So there are some parameters that define the electromagnetic wave propagation. So in this class, we are going to discuss the simplest form of the electromagnetic wave, right? So to do that, I will give a small introduction to these uniform plane waves, how and why we are considering those waves, and whether they are actually in existence or not, right? Right. So we discussed about electromagnetic waves that are created due to the varying currents and charges, right? Varying electric currents and electric charges create the electric field and the magnetic fields. And the generated electromagnetic wave will propagate in a certain velocity independent of the sources that created it. And in the last class, we discussed up to the point where we proved that the electromagnetic wave is following a wave-like behavior. So we came to the point where we derived this equation, where we showed that the Laplacian of the electric field is equal to the mu naught epsilon naught into W squared E over W T squared. So the second derivative of electric field with respect to the time. So this is the equation that we derived in the last class. So this is the equation that was very similar to the wave equation available in the physics, which was given by the equation where the displacement of the wave of a certain wave is equal to the it's 1 over velocity squared, and its displacement over per the second derivation of with respect to the time. So this is the classical equation that is available in physics, that shows us that a certain wave is propagating in a certain medium with a certain velocity v. So this same type of equation is available for the electric field, and that equation is what we we derived using the Maxwell's laws in the last class. So we can derive the same type of equation for the magnetic fields also. So we can derive the same type of equation using the Maxwell's law for the magnetic laws like this. So using the similar theorems, we can derive the fact that magnetic field also follows the wave-like behavior, and it can be written like this. Also, since right, so we can derive this equation using Maxwell's law. So if you want, I can derive it. It's not going to take much time. So using the Maxwell's law, the curl of B equal to mu naught epsilon naught dabba E over dabba T. I can take the curl on both sides. I can take the curl on both sides. I will take the curl on both sides and I will be left with this expression. And then I will take the curl inside this derivation function. So I will take the curl inside this derivation operation and I will have the curl inside here. And then I will be left with this. So using the mathematics, I can solve this expression into a simpler form where I can write this as minus uh, uh, delta B minus the Laplacian of the B equals mu naught epsilon naught, and I'm left with this cross product of E over dabba T. So this one I can write as I can write this as dabba B over dabba T using the Faraday's law, and then I can law, and then I also have the dabba over dabba T which was earlier there. So therefore this is going to be second order differentiation, right? If it is not clear, you can let me know. So this curl of E I can write as minus dabba B over dabba T. So once I take the twice the differentiation operation, I get the second order of the differentiation. So I'm left with these expressions on both sides. So in this side, I have the dot of B. So dot of B is equal to 0. The reason is that there are no magnetic flux that is coming out of a certain closed surface when there's no magnetic monopoles. And we took this as one assumption in our calculations, and this is this is second Maxwell's law. This is a Maxwell's law, and which is a Gaussian law. Gaussian law related to the magnetic field, and using this we can using this assumption we can simplify this expression further, and we are left with something like this. We are left with this Laplacian B equals mu naught epsilon naught dabba squared B over dabba T squared. So anyway, since we have minus signs on both sides, we can cancel out the minus signs. And once we cancel out the minus sign on both sides, we are left with this expression. right? So we are left with this expression finally by solving those equations. So that also shows us that the magnetic field is following a certain wave-like behavior uh, once it is once it is propagating as an electromagnetic wave in the space along with the electric field. So those are the conclusions that we derived in the last class. So apart from that, once you take this equation, right? This equation regarding the magnetic fields, since this magnetic field, since B is magnetic flux density, this is magnetic flux density, right? So since we are normally working with magnetic field intensity, we normally try to use the symbol H in the normal in normal situations, we try to denote the magnetic field in our equations. So we can actually substitute mu naught H to this equation, and we can derive the equation for the magnetic field, saying that we can write, instead of B, we can write H, because mu naught is a constant. So we can cancel out the effect of mu naught on both sides, and we can write in terms of H, or magnetic field intensity, or magnetic field, uh, this equation, right? So this is magnetic field intensity. Okay, so we call this magnetic field or magnetic field intensity. So both words are used in books. I use the word electric field in the electric field section. So you can just use the magnetic field term to show the strength of magnetic field at a certain point in space due to a certain source that is creating a magnetic field, right? So anyway, we are going to replace the B with H, since we can actually cancel out the effect of mu naught on both sides, and we can have H only on both sides. So mu naught, actually I take, considering that this is a free space, so in most of the calculations I'm doing here, I'm assuming it is free space, and I'm doing the calculations regarding the free space. But you can always add the effect of the medium by taking into consideration the relative permittivity and the permeability parameters. And by using those parameters in this equation, you can convert this into an equation that is used for a certain medium. So right? So this is the equation that we derived in the last class, right? So in today's class, we are going to study the simplest form of the electromagnetic wave that can occur, and we are going to yeah. So I mean, it's like a constant, right? So if you even if you like, so why are you saying? Yeah. So substituting means like I'm putting mu naught H here, yeah, and mu naught H here. So what are you saying? I mean, where should I add the additional mu naught? Onto the left side? Why are you saying like that? What is the operation happening here? Yeah, Laplacian. Yeah, Laplacian function. So that means like the square root of the differentiation with respect to x, y, and z, right? So so these functions, these operations, do they affect the mu naught? Do they affect the mu naught? It's a constant. This is a operation, differentiation operation done on this B. If B has some constant, I can take it out, right? Because I'm doing differentiation. So using under the principles of differentiation, the constant comes out. No, in here, this is Laplacian. So in the last class and the class before, we discussed the fact that a varying current in a certain conductor can create an electromagnetic wave, right? So when the current is varying and the current is moving up and down, certain electromagnetic wave is generating in a certain direction. So if we take, for example, this is the electromagnetic wave that is generating, right? And the source is around here, right? The source of our current is around here. So let's say the current is going down and going up. So it is going down and going up, right? Current is, it is first going down and then it is going up. So based on the variation of the current and its direction, the electric field is created. And because of the electric field, corresponding magnetic field is created. So if we assume that a certain source is creating this, certain source is creating this current, and this current is somewhere here. So let's say the source of the source where the electromagnetic wave is created is here. The amount of energy that is available around this area is very high, right? So when it's very near to the source, the amount of energy that is created around this source is very high. So we normally denote that uh, we have high energy near the source. So near the source, we have uh, higher energy than once we are moving to large distances. And near the source, the wave is, if we have a source like this, and if we are only sending current in a metal conductor like this, right? Let's say this is a metal conductor, very simple metal conductor, where we are sending the current up and down. Then in this situation, the wave is generated in all directions, right? We discussed this in one of the previous classes. The wave is generated in all directions around the conductor, right? So let's say, no, if I'm going to draw it, I will be able to draw that other waves are going in all the other directions as well, right? So because of that, we will be having a higher density of waves generated very near to the source. We have a very high density of waves near the source, right? So we have the waves are generated with very small distance, small gap between them near the source. So because of that, the amount of energy that we see near the source is very high. So we have waves like this, which are going in all directions. The waves are moving in all directions, right? Near the source. And all directions, and near the source, the energy, the radiation energy, the available energy is high. The energy that we can observe, or the radiation, we call it, the energy that we can observe due to this wave propagation, which we call as radiation, is very high, right? So the radiation, if we try to measure the radiation will be propagating in a sphere-like manner, like a spherical shape around the source. So if I'm going to draw that energy near the source is somewhere like this. If the source is a metal conductor that is generating the electric and magnetic fields, then the amount of energy that we have around that source is spreading along a certain sphere around the source. Yeah, I mean, yeah. So that is yeah. So in these places, I mean, exactly in this top position and in the down bottom position, electric and magnetic fields are not generated because we are taking our electric field generation along the right hand side rules, and the direction will be in these kind of planes, So the electric and magnetic fields will be available in these kind of planes along the sphere, right? So these planes are determined using the right hand rule, and the amount of electric and magnetic fields generated in those places are determined by the current that is going through this conductor. So so based on the electric and magnetic fields that are generated, the radiation energy will change on top of this sphere, and the energy reduces as we move along the let's say one axis, move along. If we move along z-axis, the radiation energy reduces, and the radiation energy, the radiation energy sphere also enlarges, and the amount of curvature in the sphere is kind of getting to a place that the curvature of the sphere at this point, for example, is almost like a plane, right? So the sphere is too large that we can approximate the curvature of the sphere as a plane, uh, like a straight plane which has less curvature. So we can assume that the electric field and magnetic fields that are generated at a distance very far from the source lies on a plane, right? So the electric and magnetic fields, yeah, perpendicular to the z-axis, electric and magnetic fields that are generated very far from the source, lie on a plane with low curvature, right? With very low curvature, and therefore we can assume that plane to be a very so we can plane is a straight plane, right? The plane is a straight plane, like a plane with less curvature. So under that scenario, we are going to analyze the electromagnetic wave that is generating at that location, right? So the reason that we are doing it is that it is the easiest way to analyze the electromagnetic wave, and it is the most simplest way that we can analyze the electromagnetic wave. So if we can generate mathematical models for the simplest electromagnetic wave, then we can use that theory to develop mathematical models for the other types of waves that are generated in this field, so in this environment. So in order to do complex things, first we need to model the simplest form of the electromagnetic wave. So the simplest form of electromagnetic wave that is generated can be observed at a very far location from the source, right? So if the source is here, if we are observing at a very far location from the source, we can observe this kind of a wave from a very far location from the source, right? We can observe a type of a wave that we are going to study. So this type of a wave is known as the simplest type of electromagnetic waves, and those type of waves are known as uniform plane waves, right? So we are going to discuss about uniform plane waves, and we are going to analyze its parameters. So I'm going to erase this. So we are going to discuss about the uniform plane waves. Right? So the waves uh, uh, the waves that occur at uh, long distances from the source, source uh, become uh, plane waves due to the due to the uh, transition of due to the transition of the uh, uh, due to the transition of the waves from spherical nature to uh, planar waves, planar uh, planar nature, let's say, right? So because of the spherical transition from the spherical nature up to the planar nature, once the electromagnetic wave is traveling over a long distance from the source, the waves become plane waves, uh, and the waves are uh, waves are waves are observed to lie on a certain plane. So it is something that happens at a large distance only from the source. So we can observe. Yeah, infinity or very large distance from the source. So one example is that the sun and the earth, let's say. So the sun is producing a lot of energy. So around the source, around the sun, there's a huge amount of radiation and energy, and that energy is spreading in all directions in a spherical shape around the sun. But since the distance from the sun and the earth is very large, there are so many miles. So from the sun to the earth, so by the time that the electromagnetic waves are approaching the earth, the waves are seen to move in a certain way that behave like the plane waves that we are going to talk about. So the waves are known to be planar waves. So the waves are going to move with certain like amplitude, certain frequency, and with certain wavelength and so on. So if the wave is traveling in a vacuum, the wave is not having much attenuation. So until the atmosphere, until reaching the atmosphere, until it is moving in the vacuum, the wave will be having a certain constant amplitude and constant frequency. Until after it reaches the medium, the atmosphere, and some kind of medium on the Earth's surface, then the attenuation will occur and the wave will reduce its amplitude and maybe its frequency and other parameters with the time. So it will decay over time. However, near the Earth's surface, up to the point where we have vacuum, we can assume that the wave is following a certain constant amplitude, constant frequency nature. So the wave we are going to analyze is that wave which has constant amplitude and constant frequency, constant velocity, and so on. Okay. So that wave we call as uniform plane wave. So we are going to derive some mathematical equations related to that. We are going to make some assumptions, and we are going to derive the properties of uniform plane wave by doing that. No, plane is like a small portion of the sphere's surface, just a small portion only. So we are not taking the entire Earth. Then it's again a curved plane. It's not a curved one we are selecting. We are only considering a very straight plane to analyze. Yeah, maybe in the equator somewhere where we can consider the plane is very straight. Right? So in the last class we stopped with the wave equation, right? So we are using the wave equation, and we are trying to solve the wave equation. Uh, uh, we are trying to solve the wave equation, assuming the conditions of this uniform plane wave, right? So if you have any questions, you can ask up to now. Right. So once we are analyzing the plane waves, we are assuming some conditions, right? So we are assuming some conditions, the following conditions. Once we are analyzing the uniform plane waves, right? We are assuming the following conditions. So the first condition is that both the electric and magnetic fields, I will write H as the magnetic field, right? So B is the magnetic flux density, H is the magnetic field, right? So both E and H are depending only on the coordinate axis Z, right? So are depending only on the axis along which the wave is propagating. Okay, so depending only on the axis along which the wave is propagating. So what is the reason to making this assumption? Along which the wave is propagating. So in this case, we are assuming that the wave is propagating along Z direction, right? So we are assuming, so along Z coordinates only. So, right, so along Z coordinates only, the both E and H are depending, or E and H are functions of Z, right? So we are saying that electric field and the magnetic field are functions of Z, right? So what is the reason to say this? Why do we say that electric and magnetic fields are only functions of Z and not functions of X and Y? Why are we saying it is not varying along X and Y? Yeah, so at one point that we consider, at one plane that we are consider, uh, the uh, the electric field and the magnetic field are having a constant amplitude, some constant amplitude and direction, right? So if that constant amplitude is changing, then that amplitude change, uh, sorry, yeah. So once the certain amplitude is created, it will remain constant in that plane, right? So it won't keep on increasing because it's against the energy conservation. So the electric field, magnetic field, they do not change over this X and Y directions. So if we have X direction over here, X direction over here, and the Y direction over here, the amount of electric field and magnetic field, let's say electric field is only generating along the X direction, then we have certain amplitude over X direction, EX. And if we have a magnetic field creating along Y direction, then we have HY along the Y direction. So if we have electric field and magnetic field created at a certain direction and amplitude on this plane, the amplitudes will not change on that plane, right? The therefore this assumption is saying that electric field and magnetic field are not depending on X and Y coordinates, right? X and Y coordinates, but it will depend on Z because it is moving along Z. Just because it is moving along Z, the electric field is depending on Z, just depending on Z. It's not changing its amplitude over Z, but it depends on Z. I mean, it will change its amplitude if it is moving within a certain medium. But if we assume this wave is moving in the free space, then the amplitude won't change even if it is moving along the Z direction. So the electric fields, location, its distance, its direction is defined using the Z coordinates and the time coordinate, the time at which time, at which location this electric field is there. And likewise, we can define the electric field's location and the time at which the electric field is and the magnetic field is available using the coordinates Z and the time parameter T. Right. So therefore, E and H will be functions of Z and T actually at the time. Right. So the we can write as E as functions of Z and T, H as functions of Z and T. So we need to keep this as our basic assumption once we are trying to analyze the wave which is formed at this location, which is on the plane. I mean, the electromagnetic wave that is generated due to the fields available on this plane and propagating in the Z direction, right? And the second assumption is that these fields are available in a certain homogeneous and a lossless medium with certain parameters of permittivity and permeability, right? So that also I will try to write. So the E and F, E and H fields exist in a homogeneous medium, homogeneous lossless medium with parameters epsilon and mu naught, which are above zero. So the values of epsilon and mu are going to be above zero, or they are going to have some finite value, and the conductivity or the electric conductivity is going to be zero. Right, so the free electric charges are going to be zero in that medium, right? So the wave that is generated is propagating in a homogeneous lossless medium, right? And the medium has some parameters that define its medium qualities. So the epsilon and mu define the medium's qualities, and uh, the lossless term, what does it mean? Yeah, doesn't attenuate. The wave doesn't attenuate, right? So the attenuation does not happen. So therefore, the amplitude of the wave will remain constant in this space. We are just going to assume for a free space, right? And then we can apply it for other mediums. Since we are only analyzing the very simplest form, we are assuming that the wave doesn't attenuate during this in this medium. So abstract means, so permittivity means the ability to create and store energy in the medium. It doesn't have any ability to store the energy or to absorb energy from the wave, then it doesn't do anything to the wave. So with these two assumptions, I will try to write some equations that I will use to that I will use to obtain some equations related to these uniform plane waves, right? So these are the two assumptions that we are going to make. So the wave is going along, going in a homogeneous lossless medium, and the electric and magnetic fields are depending only on the axis along which the wave is propagating. So the wave is going in the Z coordinate axis, and the functions of electric and magnetic fields are depending only on Z and T. So based on this and the wave equation that we derived earlier, we can derive some conclusions about the uniform plane waves, right? So by applying the knowledge we have on, and the assumptions that we have regarding the uh, the uniform plane waves and the wave equation we have, we can derive some equations, right? So first and foremost, in the wave equation, uh, we derived earlier, we can write that wave equation like this, right? So Laplacian of E is equal to mu naught epsilon naught W squared over W T squared, right? So this equation that we have derived earlier, right? So now what we are going to do is we are going to simplify this equation a little bit by considering only the x component of the electric field, and applying that component in this equation, right? So we are only going to consider the x component of electric field in this plane, and we are going to apply that x component of the electric field into this equation, right? So x component of the electric field I'm taking, and I'm going to apply that only into this equation, right? So I can do the same thing for the y component of the electric field, and I can derive the equations related to that also. So since I'm going to like use the similarity principles and I'm going to derive those equations, I'm only going to consider the x component and derive these equations. And after I have got some equations and results, I will apply that same outputs to the other equations. So this is the equation that I will get if I consider only the x component of the electric field, which lies on the plane that I'm considering. Okay. So once I have this equation, I need to find the solution to this equation. So I want to find the solution to this equation, right? So in order to find the solution, I can expand this equation. I can expand this equation by expanding this operation, the Laplacian operation. So Laplacian operation is this, right? So we can denote this Laplacian operation by this expression, right? And then I can write Ex is a T, and the other parts are the same. Right? So if I have a equation like this, and since I have the electric field function varying along z and varying on these two parameters only, then the differentiation with respect to x and y are going to be what? 0, right? It's going to be 0. So only I have only this component remaining where the differentiation with respect to z is taken. So only this equation will remain, right? And then so based on the mathematics, the solution to this equation will be of the form where the electric field will be sinusoidal in nature. Sinusoidal, and it can be denoted using cosine function, which varies like this. So the electric field which is moving forward is given by E plus, and the electric field component which is moving backward is given by E minus. So this is the equation that gives a general solution to this A equation. So the general solution is this one, and this denotes that there are two waves that are generating, forward wave and the backward wave, right? So in our calculations, we are only going to consider the forward wave, and we are going to consider the forward wave and its characteristics. So so the forward wave I can denote using some phasors, and by taking the real part of the phasors, I can analyze the forward wave component of this electric field, right? So since the time is over, I will try to stop, right? So do you have any questions so far? I mean, it is the general solution for these kind of differential equations with second derivation. So mathematically, you can find the like for quadratic equations or some differentiation equations like this with the second order, the solution is like this. So mathematically, the solution is, yeah, it is the addition of two sinusoids, which we can denote using cosine signals.